Hello friends, this is Praveen. In this video, we will see the questions asked in GATE 2018 exam from subject Electronics and Communication Engineering. Here we will see the questions from topic Digital Circuits. For the questions from others topic, please find the playlist available on my YouTube channel. So here we will start. Our first question is, a function f of a, b, c defined by three Boolean variables a, b and c when expressed as sum of products is given by. So here sum of products is given where three mean terms are given, where a bar, b bar and c bar are the complements of the respective variables. The product of sums QS form of the function f is. So here we have to write the equivalent form of f, but in product of sum form. So here mean terms are given. F is equal to summation of mean terms, and this a bar, b bar, c bar represent to 0 0 0 means this first combination 0. A bar, b, c bar represent to 0 1 0 means 2, and this is a, b bar, c bar means 1 0 0, that is 4. This is equal to the max terms. We can write it as pi capital M, and the remaining terms 1 3 5 6 and 7. All this you can represent also in K-map, so it would be easy to realize the terms. So here I will draw the three variable K-map first. So here assume this is for A and this is for B, C. So this is 0 0 0 1 1 1 1 0, and this is for 0 and 1. A bar, B bar, C bar, so there would be 1 at this position. A bar, B, C bar means 0 1 0 0 1 0, so here it would be 1. And A, B bar, C bar, A, B bar, C bar, this is 1, and remaining will fill as 0. So now the product of some form will represent to this zeros terms. So here for first these zeros will write here this would be A plus B plus C bar. Here noted point is that we are writing the product of some form. So here 0 will dominate. For next 0 it is A plus B bar plus C bar. A plus B bar plus C bar. For this 0 it would be A bar plus B plus C bar. A bar plus B plus C bar. For this 0 it would be A bar plus B bar plus C bar, and the last term would be A bar plus B bar plus C. A bar plus B bar plus C. So here all these 5 terms is matched with this C option. So our C option is correct. Also you can solve with some Boolean algebra. This f you can write as f bar and its double bar, and using some De Morgan's rule you can expand, but it would be very complex to solve. So this is a very simple and direct method. So C is our correct option. Now next question is, the logic function f of xy realized by the given circuit is. First we'll consider this NMOS circuit. The input is x bar, y bar, x bar, y bar, plus this is x and y, plus x, y. So this is equal to f of x, y, and bar of this. So this is x nor of y whole bar, which is equal to x XOR y. So this is our answer, x XOR y. Also we can verify for this per half or pull-up circuit. This f of xy be equal to here x bar plus y, and from this side it would be x plus y bar. This is for PMOS. So we will write it into product of sum form. So on simplifying this and bar of this, so on simplifying this, we'll get x bar would be 0 and y bar would be 0. So it would be x bar y bar plus xy, complement of this. Again, it is the same term, so it would be equal to x bar x XOR y. So our correct option is D. Next question we have: a traffic signal cycles from green to yellow, yellow to red, and red to green. In each cycle, green is turned on for 70 seconds. So here it is given that green is turned on for 70 seconds, yellow is turned on for 5 seconds, yellow is turned on for 5 seconds, and red is turned on for 75 seconds. This traffic light has to be implemented using a finite state machine. The only input to this FSM is a clock of 5-second period. So here clock period is given of 5 seconds. The minimum number of flip-flops required to implement this finite state machine. So first we will find the total states. Total states would be equal to the total time. So its sum would be 150. So total time is 150 divided by the clock period, which is 5. So it would be 30 states. Here, to make these 30 different states or 30 different combinations of binary numbers, we will require at least 5 bits, means which will give us 2 to the power 5, means 32 combinations, which will fulfill this 30 combinations. So, and to generate this 5 bits, to generate 5 bits, we will require 5 flip-flops. So minimum number of flip-flops required to implement this finite state machine is 5. So our answer would be 5. Next question we have: a 4 variable boolean function is realized using 4 cross 1 multiplexers as shown in the figure. The minimized expression for f of u v w x is. So we know the multiplexer in which these u and v are select lines, and for 4 combinations of select lines are multiplied by their inputs, and their sum is placed at the output. So here we'll see that for these two combinations I0 and I3, the input is 0. So these two terms would be 0 at the output, and remaining terms will write this for I1, it would be 0 1, means u bar v into VCC. So VCC we consider 1 plus, next is uv bar. So this is the output of this first multiplexer, which is the input of input u0 and u1 of second multiplexer. So similarly, for this multiplexer, these two select lines have 4 possible combinations, and each combination will multiply with their inputs, and their sum will be placed at the output. So last two combinations of wx, that is I2, for this I2 and I3 is the input is 0, so that term would be 0. So here we will write only for I0 and I1, where this input is common for this, so we'll write it as it is and multiply by writing the two combinations of this w and x. So for I0 it would be w bar x bar plus, for I1 it would be 0 1, or we can write w bar x. So here we will see that this is the output f of u v w x, and it is matched with option D. So D is our correct answer. Now next question we have: the logic gates shown in the digital circuit below use strong pull down and MOS transistors for low logic level at the outputs. When the pull downs are off, high value resistors set to output logic levels to high, that is the pull ups are weak. Note that some nodes are intentionally shorted to implement wire logic. Such shorted nodes will be high only if the outputs of all the gates whose outputs are shorted are high. So here the circuit diagram, logic circuit is given. The number of distinct values of x3, x2, x1, x0 out of the 16 possible values that give y is equal to 1 is. So here simply we will find the logical expression, that would be easy to apply the combinations of these inputs. So consider this point is, this node is n. So here n would be equal to x1 XOR x2, and consider this point as m, and m is equal to, here this is x naught bar, and this AND operation is there, x naught and n. So AND operation is here. So here we'll see that x naught and x naught bar, it would be 0. So m node, there will be always 0. Now the output y we will write. So y is equal to this m plus x3. So m is 0 here. So here it would be only y is equal to x3. So here for the values of x3 is 1, then the output y will also be 1. So there in the 16 possible combinations, in 8 combinations x3 will be 1, and doesn't matter whether other bits either 0 or 1, the output of this OR gate is 1 if any one of the input is 1. So x3 is 1 for. Now here is the next question. In the circuit shown below, a positive edge triggered D flip-flop is used for sampling input data Din using clock CK. The XOR gate outputs 3.3 volts for logic high and 0 volts for logic low levels. The data bit and clock periods are equal, and the value of del T upon T clock is equal to 0.15, where the parameters del T and T clock are shown in the figure. Assume that the flip-flop and the XOR gate are ideal. If the probability of input data bit transition in each clock period is 0.3, the average value of the voltage at node X is. Here first we will draw the output waveform for this XOR gate. So here we will draw the voltage waveform. Assume initially at the output there is 1. This XOR output would be 1 when both the inputs are not same or different. So here consider if your D in is 1, and so for to make it different, our output would be 0 of this D flip-flop. So initially consider it is 1, here it is 1 and 0. Now the input is 1, and we apply the clock pulse. It is given that there is a positive edge trigger D flip-flop, and same is shown in the figure also. So when we give the positive edge trigger of the flip-flop, whatever is the at the input, it will place at the output. So it here there was input 1, it would be at the output. So here output would be also 1, and when both inputs will be 1 1, output would be 0 here. So it will change from 1 to 0 till the input changes. So here we will see the input is changed from 1 to now it is 0. So here it is 0, and it is 1 here. So 0 1, output will be again 1. Initially it was 1, then it changed to 0 for a short period, and now again it would be 1 because it is 0 here. So 0 1, it would be again 1 as input changes, and it will remain 1 till we apply the next clock pulse. As we apply the next clock pulse, the input at the D flip-flop, it will be at the output. So here from 1 it will change to 0, and here we'll see the XOR input is same, so output would be 0 here. So from 1 it would be changed to 0 again. So here it would be 0, and as the input is changes, the input changes from 0 to 1. So here we'll see it is 1, and 1 0 XOR output for input 1 0 would be 1 again. So here at the output we will get 1, and so on it carries out. At the next further at the next clock pulse, the state will be changed to be 0, and as input will be changed, the output of this XOR gate will also change. So this will get the output waveform. Here it is given in the question that XOR gate output is 3.3 volt for logic high. For logic high, the output is 3.3 volt, and for logic low, it is 0 volt. Right. So here now, if the probability of input data bit transition in each clock period is 0.3, the average value of the voltage at node X is. So here we have to find the Vx and the average value of this. So here it is our output for I is 3.3 volt is multiplied with the transition probability is given 0.3. So this will multiply with the duty cycle of this our waveform. So duty cycle is we know the duty cycle is given as on time upon total time, t on plus t off for this waveform. So here we will calculate this on. We will calculate as this is total t clock minus del t. So it would be t ck minus del t upon t on is t ck minus del t plus here off time is this equal to del t. So del t would be cancelled out, and we can write it as 1 minus del t upon t ck. Del t upon t ck is given 0.15. So here we will write it as 1 minus 0.15. Here this is tau is equal to, so it would be 0.85. We'll put the value of tau here. So it would be 3.3 into 0.3 into 0.85. So on simply solving this, we will get 0.8415. So this is our answer, output voltage. So the voltage node X, it would be up to 2 decimal places. Our answer would be 0.84. So this is our correct answer. Now next question we have. A 2 by 2 room array is built with the help of diodes as shown in the circuit below. Here W0 and W1 are signals that select the word lines, and B0 and B1 are signals that are output of the sense amplifiers based on the stored data corresponding to the bit lines during the read operation. So here during the read operation, the selected word line goes high and the other word line is in the high bit density state. As per the implementation shown in the circuit diagram above, what are the bits corresponding to Dij, where I is equal to 0 or 1 and j is equal to 0 or 1 is stored in the ROM. So here the read-only memory data is given and circuit is given. Here first we will understand that this VDD supply we are applying to the this is the gate terminal of the transistor. So as there is a gate current is present, then this transistor which is acting as a switch, it will be in on condition. So if this is on, so at this terminal there is a ground, means 0 level, and this that 0 level will be placed here. So here it would be 0, and same for this also, so it would be 0 here. Now we'll see that this W0 select line is connected to this B0 line only. So if W0 is 1, then this diode will be on, and it will change this 0 level to 1. So here it would be 1, it will change to this 0, and that 1 would be sensed by this amplifier, and this B0 will have output 1. So here we'll see that here W0 is 1, then B0 is 1. So we'll say W0 is equal to B0 here. Similarly for W1 we'll check that if W1 is 1, if this is 1, then this diode will be on, and it will change the state of this point from 0 to 1. That 1 would be sensed by the this amplifier, and now B1 would be 1 here. So here again W1 is equal to would be equal to B1. So if we uh, write the bits here, so it would be 1 0 0 1. This is W0 W1 and correspondingly BD0 and B1. So this is 1001. This would be A would be our correct option. So that's all about for this video. Here we have seen the questions asked in GATE 2018 exam from topic digital circuits. For the questions from others topic, please find the playlist available on my YouTube channel. Also, its link is given in the description of this video. So in the last, I'd like to say thanks for your kind attention. Your all suggestions are most welcome. Please like, share and comment and subscribe my channel Praveen 25488. All the best friends. Thank you very much.